Hello, welcome back. In this session, I will talk about the monotonicity of the function. We definitely recall that monotonicity of the function is checking if the function is increasing or decreasing. That's when we say that function is monotonic on the interval from A to B, if it is either increasing or decreasing. And we know the algebra definition of the increasing function. If x increase, the y increase. If x increase, then function is increasing. If x increase and y decrease, function is decreasing. Now what we will do, we will try to add the sign of the derivative. This is, we can see the increasing function. We may have a little bit different shape, but we will talk about this in the next video, next session, because this function is increasing and this one is increasing. Yeah? They are bended in a little bit different way. But let's focus on monotonicity. That means this is increasing, okay? Drawing, because tangent line is a strong tool of the calculus, drawing tangent line and just investigating the slope of the tangent line. So we can see increasing function, tangent line has the slope positive, 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 positive. Either way, if it's bended like this way or this way, if slope of the tangent is still positive, and slope of the tangent line at the particular point is the derivative. That means now let's look at this definition. If the first derivative is positive on the given interval, then function is increasing. That's how we can check the increasing intervals. From now on, in order to prove that function is increasing, we have to show that first derivative is positive. Okay, and respectively the same for the decreasing. This is the same situation. Function is decreasing. We can see the values are getting lower. Drawing a tangent line, looking at the slope. Slope, this pink lines, has a negative slope. Negative, negative. One is a little bit steeper than the other one, but negative, negative slope, negative slope, negative slope. Slope of the tangent line is the derivative. Then, if the derivative is negative, then on the given interval, then function is decreasing. Okay, that's how we will prove that function is decreasing. Really strong and solid tool. Okay, and for instance, let's just look at this really quickly. Show that function natural log of x is increasing on its domain. And domain is just the positive numbers. We know domain of the logarithmic function. And we have the graph, and yeah, like how I can prove it that this is increasing. It's definitely, we can see. But we just learn, we may look through the derivative. That means let's find the derivative. Derivative of natural log of x is 1 over x. And we can see this expression, 1 over x, is always positive, yeah, if x is positive. If x is greater than 0, because if I will substitute positive numbers, 1 over positive number is always positive number. So we can see derivative is always positive. Yes? Derivative is always positive for all x's from the domain. That means if the derivative is positive, function is increasing. And that means function is, we can see function is increasing for all x's from the domain. We know what is domain. And I think this is quite strong. It's a proof. Okay, now we will not always have that ideal situation, because function will sometimes it could be increasing, decreasing on a certain intervals. That's mean we remember this graph. Yeah. And let's look at this graph for a second. Function is increasing here, and it's increasing here, and also increasing here. I would like to maybe draw something like this, or maybe, because we also remember from the critical points. You probably know what I was trying to, let's just say horizontally, because I need that point. Okay. And now we can also see decreasing, and yeah, that's it. That's increasing. That's what we will need. We have to find the critical numbers, and we are confident with this. You practice, you went through the critical numbers video. That means the critical numbers, this critical points, these turning points, will help us to identify the intervals. That means, first of all, we need the critical numbers. And then we may test the number, which we actually have the first derivative test. Right? We can test the numbers. And I mean, we can use the first derivative test to determine the intervals for monotonicity, and then respectively, consequently, we will identify if the critical number is giving us local maximum or local minimum. And also, we may have the situation that even if we have a critical number, function is still, like, for instance, increasing. That means not all of the critical numbers will give us extreme values. That means now let's look at the first derivative test, which help us to identify lots of good things. Okay, first derivative test. Probably quite common, like result of everything what we did. That means let's suppose that C is a critical number of continuous function. That's we have to know how to find the critical numbers. And now, if derivative, if the first derivative is changing sign from positive to negative, so we can see positive is when the function is increasing, positive first derivative and then negative. Then at that critical point, function will attain local maximum. That's we have to find out where derivative is positive, where derivative is negative, and then at these changing points will be local maximum. And the same concept for local minimum. If the first derivative is changing the sign, on the left-hand side will be negative, and on the right-hand side will be positive, function will attain minimum. You can see it. And it's so intuitively, we will not make the mistake. But what we have to do, we have to test the sign of the derivative on the left and the right-hand side of the critical number. Okay, that's everything. If the derivative, we may have a critical point, we may have like, let's say horizontal tangent, and we testing the sign. If the sign of the derivative is not changed on the left and on the right hand side, then function doesn't have a local extreme value. It's still a critical number, but no local maximum, no minimum at that point, or the other way. Okay, just a summary. And now let's see. Let's take a function, polynomial, and let's identify where the function is increasing, decreasing, and local extreme values. So we can see this function is polynomial. That means it's defined everywhere. Domain is all of the real numbers. That means that's good. That's good. And we also know that derivative is defined everywhere. Yes, I mean, doesn't have this. We do not have the situation that the derivative is undefined. That's what we will need. First of all, we need critical points, critical numbers. Okay, for the critical numbers, we have to solve this. In general, that's what I was referring. We have to find out where derivative is 0 or where derivative is undefined. But in this situation, since it's not rational, we do not have this case, because derivative is defined everywhere, nice and smooth curve, polynomial. Okay, first of all, let's find the derivative. Derivative of this function 3x to the power of 4 is 12x cubed minus 12x squared minus 24x, and that's it. Okay, and we have to show that this derivative, this is 0. So maybe I can factor out 12x. We will have x squared minus x minus 2. Yeah, that means this expression must be 0. For the critical points, we have to solve it. I hope I did correct, x squared. Okay, now we have 12x, and still this quadratic can be factored out. I think 1 and 2 plus and minus. Okay, so we can see x is 0, x is negative 1, x is 2 in order to get that product 0. Okay. So we do have all of them in the domain, belongs to the domain, belongs to the domain, because domain are all of their numbers. Okay, that's the critical numbers. Okay, critical numbers, 0, negative 1 and 2. Now what we will do? First derivative test. What we can do, maybe I can put them here. We will draw a number line. We will place critical numbers, negative 1, 0, and 2. And we will test the sign of the derivative. I can put derivative. This is, for instance, good form. Product form is always good form. This is derivative either way, this line or this line. Okay, and let's test the sign. I can pick any number from these subintervals and substitute to the green box, because that's the derivative. If I substitute, for instance, 3, yeah, number greater than 2, 12 times 3, 3 plus 1 positive, 3 minus 2 positive. All of the factors are positive, then the total will be positive. Now let's substitute 1. 12 times 1, 1 plus 1 positive, 1 minus 2 will give us negative number. Then it's negative. Let's substitute that small interval, negative half. Negative half times 12, this will be negative. This will be actually positive, and this will be negative. Yeah, negative half, negative 2. Negative times negative will give us positive. And then let's substitute negative 2. Negative 2 and negative 2 is negative number, negative 4. Negative 2 plus 1, negative number, negative 2 times 12, negative. Negative times negative times negative, it's negative. Okay, that's we know the sign of the derivative. Now, first derivative test. If the first derivative is negative, function is decreasing. When it's positive, function is increasing. Decreasing, increasing. Yeah, we can see that's quite primitive graph, but so powerful. And now we can even identify the critical extreme values. Function is decreasing and then increasing. It will be, yeah, I can even draw the function. It will be local minimum at -1. And then increasing and decreasing, local maximum at 0 and local minimum at 2. Okay, and that's quite, please make sure that you know how to place this green sign. That's the sign of the derivative. And we almost have, yes, we almost have the shape of the function. We still don't know the corresponding y values, yeah, because we can see at and the increasing. Yes, I mean increasing and decreasing. That means this will be interval for increase, decrease. Okay, and the other one is for increase. Okay, that means at -2 function attains local minimum. And if we would like to find this local minimum, we have to find out the value at -1, substituting back to the original function. Okay, and then at 0, function attains local maximum, and local maximum will be the value of the function. 0 is easy because I can substitute. 0 is 5. And then at 2, function attains local minimum again. Value at 2 will be, I didn't use, I think I have on my next slide. And then intervals of increase, decrease, we just have this. I can maybe write on the next slide. Let's actually look, but what is my point? My point is that even like so fast, we did get the shape of the function. And let's look at this one. This is actually the shape of the function. Yes, we can see we have -1, 0, and this is 2. Okay, that's mean -1, 0. Oh, the value was 5. At 2, I don't know. You can check later. That's mean this will be the value at 2. Yeah, we can substitute 2. Oh, at -1 is 0. And then we can just, my screen is, okay. So I can say function is increasing on the interval from -1 to 0. Yes, we can see from -1 to 0, union from 2 to positive infinity. And function is decreasing on the interval from -infinity to -1, yeah? And then from 0 to 2. And because from 0 to 2 is increasing. Okay, that's first derivative test. Okay? And let's maybe do one more example, because now I have more examples, but you can try. You can take another function and do the same thing. Yeah, you will just follow these steps. Find the critical numbers, make sure that they are in the domain, test the sign on the left and right-hand side of the critical numbers, okay? And they not always alternate, just a side note. Okay, but now knowing, let me just, yes, I have, you can check this. I just want to, in this session, just want to solve this exercise with you. Yeah, it's kind of like backwards. It's also a good way of thinking. That means we will get what we have. We have the graph of the function, but actually this is the derivative of the function. That means this graph represents the derivative of continuous function. Then I can think that x is defined everywhere. I mean, basically from 0 to 6. Function is continuous. Yes, we have continuity. We do not have any gaps, jumps, or holes. But one more time, this is the derivative. That means this graph represents the derivative. Okay. And now we have to find out where the original function that we do not see the graph is increasing, where it's decreasing, and critical numbers, and possibly identify maxima, minima. Okay. That's what I will suggest. Yeah, do not jump to this question right away. Let's look at this. This derivative is defined everywhere. Yes, derivative is 0 at 1, 3, and let's say 5.5, 5.5. Yeah? That means if the derivative is 0, yes, if the derivative is 0, if x is 1, 3, and 5.5. That's the critical numbers. That means we do have 1, 3, and 5.5. Yeah? That means that's the critical numbers. Critical numbers. And yes, one of the, we find x coordinates of all critical numbers. Yeah? 1, 3, and 5. It's a little bit, we have to be careful. Now, let's test, yes, because increasing, decreasing, let's test the sign of this derivative. Yeah, it's mean derivative. If the graph is above the x-axis, derivative is positive. Positive. Yes, that means graph is above. I'm not looking if it's increasing or decreasing, because I'm not looking if the derivative is increasing, decreasing. I have to know where the derivative, yes, where the derivative is positive. And it's here and here. Yes, I can say it's positive on the interval from 0 to 1, and from 5.5, it's 5.5, and let's say to 6, since we only see that, okay? And this is increasing intervals. That means function is increasing. Yeah? Okay, now the derivative is below the x-axis, below, then the sign of the below of the curve below the x-axis is negative because it has negative values. That means derivative is negative. Yes, derivative is less than 0, and we may combine this actually from 1 to 5.5. We can say from 1 to 3, from 3 to, but 3 will be, we will not have extreme values. Okay, and that's what we can see. And then respectively, function that we don't really see is increasing, decreasing, decreasing, increasing. And at 1, we may notice that the behavior at 1, yes, at x equals to 1, function attains local maximum. At x equals to 5.5, function attains local minimum. Okay, it means just one more time, this is increasing intervals because derivative is, of course I am decreasing, and when the derivative is positive, this is increasing. That means function is increasing. I just didn't type this. As you can see, nice justification. But still, I did the first derivative test. That's mean, please be careful with this type of question. It's testing beautifully the first derivative test. Okay, I did one explicit example, I did one graphic example. And yes, now enjoy your monotonicity and the first derivative test. Thank you.